Right. Greetings. My name is Varaprasad, and I have the privilege of serving as the president of the Kansas State University chapter of Sigma Xi. Welcome to the Sigma Xi Outstanding K-State Scientist Award Seminar being presented by Dr. Ignacio Ciampitti. Dr. Ciampitti was born in Buenos Aires City in Argentina. He earned his bachelor's and master's degrees from the University of Buenos Aires and his PhD from Purdue University. Dr. Ciampitti is a professor of farming systems specialist in the Department of Agronomy at Kansas State University. He is also currently serves as the director of the Digital and Geospatial Tools and Farming Systems Research Consortium of the Sustainable Intensification Innovation Lab at Kansas State University. His research program focuses on integrating field statistics, remote sensing, and modeling research to understand plant responses to changing environmental factors and crop management practices. Dr. Ciampitti has published several synthesis analysis, original research and review papers on multiple crops of importance to Kansas, such as maize, soybean, sorghum, canola, and wheat. Dr. Ciampitti has authored or co-authored more than 150 refereed journal articles in the last 10 years. In addition, he has also published more than 100 extension publications. He has been extremely active in grant funding from multiple sources, and he brought in more than $8 million directly to his program, and with a total of about more than $25 million. Dr. Ciampitti has been active in training international and national students. In the last 8 years, he has trained several visiting scholars from many countries around the world, including Central America, South America, Africa, Asia, and around the world. Some of the countries include Vietnam, Cambodia, Bangladesh, Senegal, and Ethiopia. He is currently serving as a major advisor to 10 graduate students and has been in the committee of more than 20 students over the past several years. The quality of his advising and student training is evident by the number of awards his graduate students has received nationally and internationally. Currently, Dr. Ciampitti is also serving as an associate editor-in-chief of European Journal of Agronomy, and he's on the editorial board of Field Crops Research, Remote Sensing, and Forecasting journals. He's also an active member of Tri-Societies, which is American Society of Agronomy, Crop Science Society of America, and Soil Science Society of America. He is currently the board member of Crop Ecology Division of Crop Science Society of America. He has received many awards. I won't go into the details, but he has been he has won the early career awards from Agronomy, American Society of Agronomy, Crop Science Society of America, Gamma Sigma Delta, Extension Education Award, and Outstanding Research Award from many other entities. And as you all know, he was the recipient of the Outstanding K-State Scientist Award of the Sigma Xi Kansas State University chapter. With that, I will pass it on to Ignacio Ciampitti to give his seminar today, which is titled Advancing Digital Agriculture for Improving Agronomic Decisions. The floor is yours, Ignacio.
Thank you, Dr. Prasad. I hope that you can hear me okay. Thank you.
Yes, we can hear you.
Thank you very much. I appreciate it is a really great honor to really have received the award. I'm working side by side with many colleagues as Dr. Prasad and many of the colleagues that we have online. So it is a privilege and a pleasure on my side. So, and then having this opportunity and having the opportunity to provide, some insights on specifically the direction that our team is going, and then things that are getting us excited about making an impact on farmers and the people working in agriculture. So as Dr. Prasad mentioned, the title of the presentation is Advancing Digital Agriculture for Improving Agronomic Decision. And when I start thinking about the presentation, the first thing that came to my mind is briefly discuss or open myself into what is the team perspective, because many things that we do and the productivity that we have is not possible just by me or alone. And then I wanted to highlight the productivity and the team that I have behind supporting all our research efforts. I will showcase a little bit three aspects. I will present a shift of what I call a shift of paradigm. I mean, moving from what I call the traditional to quantitative agronomy. I will present a case study on exactly what is the direction on that. I will present some new research, exciting research from one of our students too, on looking about how we can start moving into data all the way to decision support tools and what are the things that we need to quantify. And I will try to close on talking a little bit about the case of digital agriculture, one case study, how digital agriculture can help us to improve phenology. And then lastly, to start thinking about how all this technology can start making an impact on farmers. I mean, so a potential solution for testing technology adoption. And closing with some ideas for the future. So with that, I would like just to start putting the people that is really the one doing all the work, which is the entire team. And I have more people. I just want to highlight many of them working on the consortium on geospatial, many of them working on different crops, but without the people on the team and really having the opportunity of mentoring young individuals and having the chance also of collaborating or working side by side with really mature professionals, postdoctoral students. So it's a pleasure. And it has been one of the greatest pleasures, I mean, in the last couple of years of really having the chance of trying to help young people and make them succeed. And maybe just to start on that, that is for what I can see that my research program I would like to be, or the potential legacy that I would like to leave behind on our research program is the personal connection to the students is really still one of the vital components of our projects. Mentoring from my side is extremely relevant, and I'm taking that very seriously. We have different ways of communicating, even when we keep everyone too busy, but we try to move in the direction of having a very open communication with all the team. I always encourage from early in the program this idea of team approach. I think that the future is not about individual scientists working on projects, but I think that the future is about how we will be able to think that many of the main problems that we have in our discipline will be solved when we start communicating and cooperating. But I'm talking about true communication and cooperation. Give you examples. Many times I have students working on 2 or 3 together in a project, and I ask them, they take different approaches and they work together using different skills. And that's what I like. I mean, the idea of working on really cooperation. Extension is a vital part of my program. If you look at all the things that we do, at the end of the day, our target, the focus of our program is really connecting and helping individuals. I really enjoy the opportunity of mentoring young people and helping them to develop as a scientist, but also I really enjoy the possibility that we can, at the same time, make an impact and benefit the society. So in many situations, extension from me is just also another way of thinking that and make sure that we have relevancy on all the things that we do. Talking to those farmers or stakeholders and trying to understand if the problems that we are addressing are things that they are worth to solve. I also believe on this motto. I mean, I call it the professional success is measured through the success of the students working on my team. And I truly believe on that. Is like, I take pride of that. I mean, I make myself more happy 10 times more when I see students getting awards or just going through obstacles and challenges. I think that when you see that, you can see a little bit of yourself or a little bit of the work that you do every day on them. And I think that that's very highly rewarding, at least from my side. And then one of the things that is not a minor point, we need to understand the responsibility that we have as scientists, that we are training the leaders of the next years, and how important it is to make sure that we train people that has a good proposition to work, cooperation, collaboration, because that's the people that we're training today. We're training the people that will make an impact for probably the next 100 years. So, and I think that I take that work and that idea very seriously, and we try to mentor as much as possible the future generation of research scientists. So trying to disclose a little bit my preference on how I work on my team, and then the importance of my team. I usually say that it's not the leader, but it's also to make sure that you have an excellent team. And then I'm very proud of saying that, yes, all the things that you will see today is just work and efforts from the team. So let me start from the first concept that I would like to discuss today, that is moving from what I call traditional to quantitative agronomy. And I think that there is nothing here that hasn't been discussed in many situations, but we need to find a way to formalize the concept. And when I talk about traditional agronomy, I discuss on this idea that there is a really wealth of knowledge. In many situations, when we talk about agronomy, or this could be applied for agriculture, we talk about what we do, what we are expert for. Many times is connected to or crop science, or weed science, or plant pathology, or entomology, is what I would call the traditional side. But the problem that we face in many situations is that we tend to work, or many of our approaches are, in some situations, are more like a silo. So we collaborate on economic analysis or remote sensing or modeling, but we truly don't do the integration. And I think that this is what the challenge looks like for the future. And in fact, I would like to see more people from the agricultural sector taking the lead and making sure that we are leading integration of our science moving forward. We start seeing a lot of projects, a lot of big opportunities, I mean, on agriculture that are basically led by all people that is outside of agriculture. And I think that we are facing some challenges on how we will be able to translate all the way from the data to the decision support tools and helping farmers. And I'm seeing that it's more an integration. So when we work on many of our projects, we start discussing about how we can make sure that we collect good field data that is on detail, and it can be reproducible, so we can move it to multiple regions. And then we start discussing with people on other teams on how we can integrate different skills. And then for sure, we are seeing that the future is on that direction on the decision support tools or systems that they are being involved. They are more complex. They require not only the genotype, the environment, and the management, but today we are talking about including the social aspect very heavily. And also we have, I mean, also not only the social aspect, I mean, involves also the cultural aspect in many situations. I mean, making sure that we include all those components into the decision support tools. I will give an example of what do I mean by traditional agronomy versus quantitative agronomy. And I will tell you exactly from experience of what happened to me in many situations. When I talk to a farmer, the farmer is asking me, what is the optimum number of plants that I need to put in this field? And in many situations, if you look at this concept of traditional agronomy, we have in mind some experiments, or we have some information, basic information, that is telling us what is the optimal plant density based on the different yield environments. So based on that, when we have a call with a farmer, the farmer is specifically asking for the question about the number. What is the number? And based on expertise and past years, we just saying, based on this type of weather environment or prediction, this will be the expected yield. And then the decision tends to be very simple, and then we just emphasize a number. So this is a quantitative agronomy that in some place, it might look like complex, but it has been and is currently being implemented by many industry folks. I mean, when they have multiple decision support tools, many times we don't get to see what is behind, but many of these decision support tools, they have behind using not only data, knowledge, information, but they have data that they use from previous yields at the county level, USDA. They use data sources from the weather information, current weather information, and forecast options of future forecasts for that environment, and also data that is connected to water availability. So basically, this idea of quantitative agronomy incorporates multiple data sources, not only just the data that is coming from previous studies and expertise, and then start adding information that we can, like in this case, I'm showing one example using some of statistics. I mean, in this case, we talk about Bayesian. Bayesian statistics is one of the approaches that can help us to get an estimate, and also the uncertainty, what is the confidence interval from that estimate. So, and the overall goal is at the end, we get some information that will tell to the farmer what are the probabilities. Okay, different scenarios of probabilities of having, depending on the water content at planting or depending on the in-season weather scenario, what are the probabilities of success and what type of risk they want to take. And then these are the type of decisions that we need to start looking into the future. So if I go to this idea and I explain a little bit more, so this is an example in a more simplified approach. You're going from the traditional static approach that in many situations is based on yield goal or experience, and then the recommendation of a number, to the next one that is more a dynamic, including the probabilistic method, and trying to get some prior knowledge, but also making sure that we have adjustments based on water conditions at planting or pre-planting. It could be a week before planting, it could be 2 weeks before planting, and then also incorporating that uncertainty coming from the forecast for the season. And then in that case, the goal is to offer the farmer the probability of what are the risk preference, and start including the economic analysis into that risk preference. I mean, in taking a higher level risk or low level of risk for taking that decision. And we are working on that. It's not something that we're saying that is a nice idea, but also we are currently working. So we have a PhD student on my team, Josefina, that she's basically working on trying to incorporate all these. And it's a challenge. It's not a simple road, because it's not only using the expertise on agronomists, but also thinking about a mathematical model and to work with a statistician, and also start opening ourselves to an economist and talk to people in computer science, because we need to run multiple change of analysis on the codes. And it's becoming quite complex, but I think that is one of the things that we want to incorporate. Is we want to incorporate the uncertainty into the process, so we can take a decision that has a level of probability. So just to give you an example how the potential probability will look like. So here is different precipitation and temperature from different conditions and different states. And when we take to look is what is the probability for one process or one of the combinations to occur during the season. The 2012 is the most contrasting growing season. There was situations with very low precipitation, high probability for low precipitation. And then if you look at the 2018 in blue points, was a better probability for much better weather conditions. So we are trying to use two really contrasting weather scenarios. And then what you finish on developing, our goal is finishing developing this type of methods, where in fact what we are doing is we're trying to start forecasting, not only predicting the past, but also forecasting the potential optimal plant density for each of the counties, for each of the regions, and also based on what is, if it was a dry season, you will see that in many situations, 2012, it was extremely dry environment. Optimal plant density was very, very low in many of the counties. If you look at 2018, another completely different scenario, you start seeing that more optimal yields. So in those situations, the probability to get high yields increase, then our optimal plant density start going up. And this is an example. It's at the county level, but this is something that we can start, if we have enough data, so we can start going down to a field level and getting this information and the probability analysis to farmers, so they can take this specific tool that has been done using past data. Now we can convert into start doing a forecast to help farmers to predict or to help take decisions, I mean, before planting. Here is one example of how, for example, if you look at the probability, the 2012 or 2018, so I will highlight one of the cases. So here, this one is for Stafford, Kansas. And you will see the difference in probability based on the year. So if we look at 2012, if we have a way to look at low water planting, a specific forecast for dry season, there was a probability of really low plant density needed for that year. And then if you look at the 50 percentile cumulative probability, you see that we were in a very low. And then if you look at 2018, that number almost was increased by double, I mean, on the optimal plant density. And then based on where we wanna provide this information to farmers, and then they can decide what type of risk they wanna get, if they wanna go in the median level, 50 percentile of the probability, or if they wanna be more aggressive, they can start pushing on the envelope on the curve, adding more plants, knowing that they might have a risk. And then in many situations, if you have more uncertainty on the weather, I mean, that will be one of the challenges when you're looking at taking a decision on probability. So that was one of the ideas, no? I mean, what is the quantitative agronomy? It's nothing different than what we have been done in the many years. So it's nothing big. It's just like thinking about how we can move from data all the way to quantify uncertainties and making sure that we can provide farmers so they can take those decisions. Similar to nitrogen, this is a second example. If you look at nitrogen in corn, how many times we have studies or research investigations discussing about nitrogen effect in corn. So we start gathering data. So this is from one of our PhD students, now Dr. Correndo, multiple studies from multiple locations. And then the basic idea of many of the research that he was conducting on his PhD was thinking about how quickly we can estimate what is the situation of the yield without nitrogen fertilization. So if you look at this curve here, and how is the type of response, and what will be the optimal, the maximum response for that environment. So many farmers face a challenge, and next year will be even more challenging, of trying to decide what is the optimal fertilization. I mean, if you look at fertilizer prices, I think that next year will be very seriously, people will start thinking about what will be the optimal. And in many cases, we need to understand that when we conduct a study, on the research side, we still have all the different scenarios. And in this case, I'm showing Bayesian as an example. I will walk through some of the steps on this analysis, but Bayesian help us to basically model all the different type of scenarios or responses that we might present for that location. And then also it help us to understand how much is that uncertain. In many situations, we have multiple studies looking at nitrogen fertilization in corn, and everyone is trying to provide a number. And then at the end of the day, they want to come up with this number that is a magical number. And we're trying to use that number applied for multiple locations. When in fact, we need to understand also what is the uncertainty. What is the basically confidence interval for the number that we are estimating? And then the overall goal at the end, once we start getting that uncertainty, thinking about the weather, how much the weather play on this. So let me walk you through this example. So here is an example, as I mentioned before, the yield response in corn to fertilization. You have what we call the V0, the situation of yield without fertilization, and we have the Y max, which is a situation with the maximum fertilization, the yield with maximum fertilization. So Bayesian is an excellent approach because it really helps us to get an estimate, but at the same time, not only just a simple estimate, it helps us to build these probability functions and probability distributions for each of the parameters of the curve. So in a simplified approach, if you think about this, what we are getting at the end of the day on this, if you look at the graphs at the bottom part of the slides, is what we call the posterior distributions. So you have the mean, the estimate, and then, which is being added all the time, is this idea of quantifying the 95% credibility interval of that estimate, which basically introduces the concept of the uncertainty of estimation. Just to give you an example, so if we want to estimate the situations in those studies that I showed before in the entire US, all the situations without fertilization. So here is an example, how well we can predict the estimate for Y0, and then the two graphs on the top for Y max. But what happens when we want to predict the uncertainty? And exactly what happens is that if we want to make a prediction on the estimate, many situations we can make predictions, using any of the data that we collected. And if you look at the root mean square error, or if you look at the relative root mean square error, the values are relatively low, less than 25%. But what happens if you start making predictions of what will be the range of variability of that number? Is that number always, if the numbers will be always on the same number, or it will be, what is the range? And if you look at the range, which is the graph that we have on the second part, the uncertainty, you will see that when we are trying to make predictions on the uncertainty, we have a lot of noise. And in many situations, the question is, how big is that noise? If you look at the Y0, the situations of yield on corn without fertilization, in some cases we have rule mean square, or just to give you an example, 1.3 megagrams. If you look at how much nitrogen means that, I mean, that could be close to 30 to 40 pounds of nitrogen. So that's the uncertainty that we could have in really predicting what would be the overall supply from the soil. So imagine that when we are making a decision or providing a recommendation, we provide one number, but in fact, we know that that number, most likely, it will have a lot of noise around the number. And it's really hard to say the number, or the most probable number might be this one, when in fact we know that it's really hard to be predicted. How hard? Well, if you look at this scenario, we were also trying to quantify what was the main factor helping us to understand this. So we have management factors in green, soil factors, and weather factors. And then what we start seeing is, for the estimate, in many situations, between the weather and the management on the Y0, we were getting a really good estimate. In many situations, I mean, for the maximum yield, the weather was the one that was defining maximum yield. And many times precipitation and radiation around flowering, it was critical. What happened with the uncertainty? The uncertainty was mainly driven by weather. So that range of variability that we say, how much is the variability on that? We can say that for the Y0, the situation without V0, without fertilization, close to 85% of that, if you look at this scenario here, 75% coming specifically from weather, a lot coming from precipitation and radiation, temperature radiation coefficient. Similar for the maximum yield. Most of the maximum yield and the uncertainty coming from the weather. So clearly highlighting the importance of weather and the importance of getting good quality, of weather data, and making use of that information that we're collecting to make decisions. So now I will shift to the last two topics that I want to highlight, that they are connected a little bit more with start using and incorporating remote sensing and some of the decisions of agronomy that we conduct. And it has been a fascinating work in really working on satellite, and then it has been evolving fantastically in the last 5 years. If you look at the first picture at the beginning of my presentation, you have seen one of the figures shows a representation of the number of satellites that they are going around the planet. And it's impressive to see how much has been evolving in the last 5 years. Here I'm showing some examples of, if I'm looking to a field, what are the potential sources of satellite I can get access today, and the resolution, and how much it changed. When I just look at the same field, going from different satellite sources. So you will see that in MODIS, because of the spatial resolution, I can barely see the field, but when I'm moving to Sentinel all the way, then I start seeing much better resolution of a farmer field, and I can see some potential problems on some of those pivots. Okay, the question that always people ask is if satellite is enough, and then I always reply, we always need an agronomist. We always need someone to go to the ground and to really check what's going on down there. And someone might say, well, satellite has been fascinating in the last 10 years. I mean, satellite has been with us for many, many decades. So the question is, what is the thing that has been evolved today, or why we are seeing that people is accepting and adopting more use of satellite? And to be honest, one of the things that we have seen that has been fascinating is just the adoption of satellites coming because we have not only more satellites compared to the last decades, more satellite options, but also we have people that they are working on the processing and giving to the farmers or to the industry immediately data that is already processed. Okay, and that's a key factor. Even if you think about the yield monitor, so the yield monitor came out in 1987. One of my first years that I have been working at K-State, I mean, I was talking with a precision ag company, and I asked them how many people knew how to use yield monitors, and they say that in many situations only 5% of their customers, they were really good on using yield monitor. And today, if you think about many people, I would say probably close to a high level of adoption rate in many situations using yield monitor, mainly because today we have access to all the digital tools like Encirca or Climate Corp or any other digital tools. That what they do is that they help farmers uploading all the information into the cloud, storing the information, and really giving you a recommendation. In many situations, you don't see exactly what's going on behind the scenes, but it's all based on automatic processing, outliers of detection, detection of outliers on the fields, cleaning of the monitor, going all the way to connect the yield data monitor with other prescription, could be fertilization or plant density, and then from there providing a recommendation to the farmer that can upload to the planter for the next year, so can use it to decide the prescription. So really moving to increasing the power of data processing and then going into the prescription. No? And this is one of the examples, I mean, of most of the Sentinel, as I highlighted there in red, and Landsat are the most used. I mean, satellite sources, if you look at side by side, Landsat versus Sentinel, clearly Sentinel has some advantage. You can see that clearly you can identify more sections of the field. In Landsat, in many situations, I mean, because of the spatial resolution, we are not able to go so much in within the field variability. But one of the things that Landsat has is more history, so relative to Sentinel that has been around only for the last couple of years. So when I work with farmers, we have this challenge. How much data is good data? And then when you look at data coming from a drone versus coming from Landsat versus coming from Sentinel, if you look at drone data, you can have basically almost a pixel per few plants. And the problem is many of these farmers don't have the machinery to make a decision and to act in such a small pixel level. So when you look at a figure that it shows so much information, many farmers decided not to tackle that. And then they feel more comfortable clearly when I show this figure from the Sentinel, where they can see that there is some variability, but there is some variability that they can handle. That based on the size of the variability, they have the equipment and they can take an action. In the drone side, in many situations, because they can detect it such a small spatial resolution, it's really hard to have, I mean, specific, I mean, action with the machinery that they have today. So maybe in the future, when this is evolving into more variable rate, into even smaller machines, potentially, there might be a solution ongoing in that direction. But today, I think that the drones are becoming much more useful today on thinking about for applying or for applying pesticides or applying herbicide in many different situations. I think that we'll be seeing more of that for drones. We try to synthesize, I mean, also emphasizing the concept of this. I mean, we put a publication, one of my members of the team, Luciana, is finishing a PhD. Sebastian also is now a postdoc in Illinois. So we have several members helping us, and we have a publication trying to synthesize some of the use of satellite in agronomy. And now moving into what is next, what is coming. So here is one of the examples on other things that we're working today and how we're trying to translate data into decisions. So here is some data that we have, I mean, in collaboration with CropQuest, I mean, and then here is showing us all the fields that has been collected in Kansas for the last several years on phenology in corn. And then what we start testing is how well satellite can help us to predict phenology. And I think that when you start thinking about the implications about that, the implications connected to management are tremendous. And then one of the things that we start exploring is how well we can start using this source and connect it to some weather information. So, and then we developed like some kind of a partnership on this partnership with Planet. So Planet is one of the largest, I mean, companies industry on satellite provided around the globe. And then when we're thinking about phenology, so Luciana also was working on putting this together, and then you start thinking about all the implications that we have from the policy side, from the irrigation, you know, in terms of basically water conservation, from the markets, from even official crop estimation. 2 or 3 weeks ago, there has been announced a partnership between NASA and USDA. So that shows basically where the direction of the science is going, no? And why? Well, because of this. One of the main challenges that we face many times is that if you look at the the current USDA reporting progress is very subjective, quite subjective. And then if you think about this one example of a report progress, just to illustrate for those that are not too familiar, of different regions on the state and how much percentage of the crop is at different moments at different percentages. But most of these, I mean, are just weekly visual inspections, or they are phone calls from the office, or now in Kansas City, in the past in Washington, and then just asking someone how the crop looks like. And that was the discussion. Can you tell me how the crops look like in your neighborhood? And maybe you probably didn't even go out and you say, it looks, I mean, yeah, from the window looks quite good. But we have, I mean, the information is about advancing, and then one of the things that the way that it's moving forward is going on this direction. It's going on the direction that we know that there is a relationship between a vegetation index all the way and the spectral signature from, and the spectral firm from corn is always up around flowering time, and then it goes down. So we know that we can start tracking phenology in multiple places. I mean, just by knowing when was more or less that corn planted, and then, I mean, by looking at that spectral signature and vegetation index over time. And this is one of the things that one of our students is working on developing really this test. And one of the things that she was working on is looking at one specific new product that is from Planet, that is a daily satellite information. So they are developing a daily satellite that is coming from Data Fusion. So, and then what this shows is a correlation matrix that basically has like the true and the predictive phenology. And then what you will get to see in many situations is that we are able, if you look at the what we call recall and precision values, we're always able to have really high precision to estimate each of the stages. And if you look at another type of satellite, we have always problems because we have less access to temporal data, because we have less access to even problems on the sensor or clouds, I mean, conditions. So this is just how quickly satellite is evolving. And it's really helping us to provide data. Now we have the data in our hands to start converting this data into decisions, to connect the data to all the way to take a decision. It is impressive to see this kind of a daily gap-free image with the Data Fusion products. It's really, I mean, for us was always a reminder of the importance of the ground truthing. For us, the field observations is what is becoming a problem. And it's also nice to see that even when you discuss with remote sensing people, geography people, they start emphasizing the importance of the protocol for data collection on the ground, and then having really good ground truthing data. So I think that emphasize the importance of agronomists and agriculture people on how we are collecting data from the ground and how we can start improve that data collection process. And yes, for sure, these type of projects is something that not only relevant for the US, but also we are looking at, I mean, there are different projects that we are exploring right now in different sections. So not only for corn alone, so there are multiple opportunities to expand to multiple crops. And as I mentioned before, just by looking at the importance of the last news on NASA partnership with USDA for the crop conditions, I think that's reflecting what we are planning to expect or seeing on the next coming years. And then just to close a little bit on this presentation, I would like to show very briefly some of the ideas on how we are integrating or crop modeling with remote sensing, and also start thinking about how we can start testing technology adoption in different fields. And there is a concept that we start developing that is called this idea of the yield persistency. And someone might also call this as a yield memory, which we say that each individual field has a memory. What is a memory means that in many situations, some of the variability and the low yielding environments versus the high yielding environments, they tend to be predicted over time. In this situation, I will show the first example that you will see that year one, this is a field, has high variability, year two, high variability, year three, high variability, but you will get to see, if we assume that the blue is low yielding, this section of the low yielding is changing over time. So we have a high variability, but we have very low ability to predict where the low yielding section of the field will be next year. Now we start seeing how this is changing. Here is another example that we have that variability, high variability in the field, but look at what happens on year 2 and look what happens on the next year. So now we have a high ability to predict, okay? And then why? Well, in many situations could be connected to soil factors. It could be connected to soil compaction. It could be connected to pH problems that basically make that variability always being high to be predicted. And then we can start developing this type of concept for most of the fields that we have available. I mean, here, and this is one of the ideas that you start thinking about. If I need to start recommending technology adoption, what would be the best place where technology adoption can make a difference, right? And here's an example here for the state of Iowa. If you look at all the fields, so we are basically start mapping some of those fields that we are collaborating and did this a couple of years ago, even for yield estimation. So, and then one of the big concepts when we start working on this is to try to make an estimate on what are the different crops and where are those crops located. It sounds a little bit silly, no? Because someone might say, do we need to have? Yes, we need to have what we call the crop mapping layer, which is the first step. In fact, a couple of years ago, we worked with on a project on Vietnam. For the first time, we tried to develop this kind of a crop layer for corn in that country. So, and very hard, challenging, because corn is grown in multiple small sections, small acres, and it's not, as you can see here, that is widespread in many states. But this is what basically for Kansas, if you think about our corn number of acres and the corn surface, I mean, it looks like, no? This is what we can see that is coming from data from USDA, what we call the observe, the CDL layer, the crop data layer from USDA. And this is what we can predict using the satellite. So if you look at the two images, I think that you can see that we are quite close. I mean, on satellite, we can make predictions on the go on our corn acres. Why I'm saying on the go? Because many times we need to expect 6 months until close to February. USDA will release what is basically the specific corn data layer for Kansas for 2021, which will be released in February 2022. But this shows the importance of doing a mapping on the go and trying to identify all the number of corn acres in the state. And then here what we try to do is to make predictions of how well we can start predicting yields. So, and then we use different indexes, vegetation indices like AV or NDVI, that are basically combining different spectral bands. And the main idea was just to also, again, demonstrate the importance of getting some good weather information. So if you look at just using satellite alone, we still have a lot of noise and low level of predictability in some sections. When we start adding weather variables like precipitation, maximum minimum temperature, then that information was really helping us to improve that prediction substantially. And not only that, we also moved into an idea that was, can we make predictions for the state of corn yield? And many situations, if you think about USDA released the yield predictions around the first week of August, we wanted to understand if we can make predictions before. Usually the predictions from USDA for corn yield, the entire US, is around August 12th. And we start making predictions to see how much of an error we have if we make predictions before that time. And you will see that in many situations, if I show all the figures, you will see that if we are making predictions by July 7th, which is this point here, and this graph here, we have very low error, one of the lowest error for making the predictions. So, and then we are anticipating at least 2 weeks the release of predictions on corn yields before USDA, and with a really high, still very high level of low uncertainty. Because if we go earlier, then early we have more uncertainty coming from the weather conditions around pollination. So this is an example of how the satellite combines, but still we need to have agronomy decisions on thinking about what is the best optimal time and trying to get these decisions, I mean, to start making forecasts. Not only on forecasts at the region level, but also we can make forecasts at the field level. So we work with many farmers across the state. We got data from farmers, and then we start asking ourselves the question of, can we make predictions on yield before harvest? And what happens to those farmers that they don't have a yield monitor data set, or they don't have any yield data from the last years? And then here we show just one example, in this case using Sentinel, of basically the prediction done with before, I mean, after flowering time, a month before harvest, versus what happens after harvest. Similar on another farmer field, always working with farmers to collect this data and showing the relevancy of how well we can predict in many situations quite well, where are the low spots and where we might see low yields in the field connected to where we are seeing around harvest time. So in many situations, we were collected for this study close to more than 20 yield monitors. So working with at least 10 different farmers in central Kansas. So, and then we start showing that some of this information satellite can help us not only just to understand the variability within the field, but also to make predictions for a forecast in the next coming month before harvest. And then just to simplify, or at least to showcase another example of how satellite can be used, this is, I mean, from data from Brazil, I mean, just also working, showing some of the international work on seeing what happens if you don't have any yield monitor. So here is an example of one field using a yield map and creating different zones based on the variability of yield. And here is another situation that we are showing no using the yield monitor and you're only using satellite. And then it shows very clearly that you can really predict quite well those different sections of the field. To close on this section, I mean, and to close on this resilient section is like, we start developing this concept of resilient systems, where systems that they basically can come up after a drought, and systems that basically are hard to predict and they're less resilient. That they basically show that when we have a stress conditions, they are really changing on the prediction. So this is a very long concept. I mean, I'm not planning to unfold all the concept today, but I'm planning to show some of the things that we are working on this. And we have a publication that is getting close out, specifically showing the spatial, all these sections of the fields that they are basically low yielding, how they are changing. Here is one field and showing different years, and you will see how these pixels are changing. In this case, we have high variability, but high persistency, so high yield memory. So those pixels are always in similar place. And then you see an example like this one, where we have basically that lack of, in some situations, that spatial pattern persistency. We have this section high, low, and then we have this section here. So every year it's really hard to be predicted. So for us, the question is, if I need to invest in technology, which one is the best candidate field? No, and we need to start thinking about where will be the place that I can get more return of investment, in the place that I have more persistency that I can predict, or on those fields that I have less persistency, that they have too much variability. And to close, because this is something that I'm very proud in the sense of all the work that we're doing. So Dr. Prasad mentioned, so we start this journey of really leading some changes on adding some data science and digital side on many countries. So we're working with many people in Senegal, Bangladesh, and also in Cambodia, and trying to develop some concepts that they could be quite simple, but trying to think about how we can start integrating data to take decisions. So this is an example of basically farmers in Bangladesh. So this picture came from IRRI, and it shows the complexity on those countries. And it shows really how much we can make an impact if we really do a good job on helping, on providing all the expertise that we have from our side, thinking about how we are combining different data sources to start getting a solution. And some things at the beginning can be quite simple. One of the examples that we just finished is using some data from one polder, from one small section in the coastal of Bangladesh, that they were the complexity on those environments is salinity. And salinity is something that is quite complex. And trying to understand how the different factors between elevation, precipitation, and salinity play, and thinking about from the beginning, what is the best crop option for the summer? Just as simple as that, no? And here is just one of the examples that we use some of the data collected from the field on salinity, and then we add some crop modeling information. These two of the postdocs working in our team also leading this complex study. And it shows that in many situations, if you look at this analysis for dry season, for high salinity environments in this region, in many farmers that were using maize, corn. For corn, in many situations, is not too stable to salinity. And if you are thinking about when high salinity, then you need to start thinking about other crops options like sunflower or magni. So here is another example of how we can start integrating data to just to get a decision on the crop choice. So future, yeah, is like the future is very bright. I think that we will have more data, and then I think that will be a challenge in our side to start thinking about how we use the data. We have new data science algorithm. We have new platform on remote sensing. We have new ideas of data fusion or different models. We have new satellite constellations. Just an example, as I showed before, this new high resolution temporal data. If you look at this data, it's a daily data. And this year is coming with eight spectral bands. So we have many different launches of satellites every week almost. So. And then to close, I want to just leave this message. It's like, I truly believe on the concept of doing more transdisciplinary research. I think that that's the future. I mean, thinking about how we are combining, integrating agronomists and statisticians and economists and practitioners, and really building that effective decision support tools. I think that we need to incorporate the support tools that they have real world concerns, but also that they incorporate uncertainty. And here again, highlighting all the research team, and then I appreciate the effort of the team and how basically, I mean, they show all the things that we can do and keep training the future generations is our task. So with that, I appreciate the time and thanks for the opportunity to present this topic.
Thank you, Ignacio, for your nice presentations. So if you have any questions, please put it in the chat box or unmute yourself and ask the question. We have about 2 or 3 minutes for a question. Let me get started while people are thinking about the questions, Ignacio. So you mentioned that the majority of the estimate of yield or uncertainty is based on the weather, right? So but how close are we to have a better quality of weather predictions, short-term weather predictions, so that we can give a better idea to manage the field to farmers?
Yeah, I mean, it's an excellent question. Sorry, let me go back. It's an excellent question. I think that I think that we still need to move research investments on weather. I mean, in fact, I mean, I think that in Kansas we are taking the lead on investing on more weather stations. And in many situations, you get to see that it's a problem. If you look at a county, we have one weather station that is in the middle. And then in many situations, we are trying to use that weather station to try to make a predictions around the entire county. So to answer the question, in many cases, we have today much better remote sensing data or other type of data sets. I mean, but we are lacking on having good quality of weather information. And then I think that even more importantly too, is I think that we are lacking in some situations to have really good quality of ground truthing data, field and soils data. If you look at the soils too, I mean, in many situations, we have very poor data coming from soils, and we don't have the same type of resolution that we can obtain from a satellite. And in many situations, we are using some soil data that it has a really poor resolution and is not precise at all.
Thank you. There's another question in the chat. How do producers respond to estimates of uncertainty? Do they make different decisions?
I have two short stories. I tried to discuss with one farmer about uncertainties, and then I lecture the farmer. I will say maybe lecture. Then he lectured me for half an hour, and then at the end he asked me, "Okay, what is the number that I need to use?" So it will take us longer than just discussing the uncertainties. I think that at the end of the day, imagine that this has been done for many, at least a century or more than a century, that we take all this research and the science that we do, and we try to simplify in a number. And sometimes that's a good thing, because we try to keep things very simple, but also in some way, I feel that undermines some of the science and our work, because it doesn't show all the research and the complexity that we really produce. And I think that we need to offer scenarios. If you look at some of the new tools from industry, you will see that in many situations, they start moving on the direction of giving you the estimate and then showing you what is the confidence interval for the estimate. For a farmer, in many situations, when I talk to a progressive farmer, and this happened a couple of months ago, the farmer appreciated very much when I mentioned to him that for the estimate on the plant density that I was providing to him, there was an uncertainty of, in many situations, it was like 5,000 plants around the number. And that gives to him the opportunity of deciding if he wants to play more conservative, and if he wants to basically play more conservative and make sure that he use a lower density, be more defensive, or if he wants to be more aggressive and take another step. And I think that we are trying to leave the decision to the farmer. We are only providing the data and the probabilities, but we want to make sure that we leave the opportunity for the farmers to take that decision.
All right, so there's one more question, and then we'll take that, and then quick response as well.
Yeah.
So can you use modeling to evaluate varieties that are more drought or high temperature tolerant?
Yes, I didn't have enough time, but let me simplify. We have a project and a study that also from one of our postdocs that we were doing like what we call an envirotyping. Envirotyping was just using all the sorghum data from many sections of the state. We were defining what is the probability to have a drought early season or after flowering, and what was the probability to have a heat early season after flowering. And the first thing that we did was to define those environments. And then once you start defining the environments, you will see and classify the environments based on these type of probabilities. Then you will see what is the overall impact on yield. And based on that, you can start making better decisions, because then you will see if this environment never have a probability of drought after flowering, should I use it to conduct a drought study? Or should I use it to put all my hybrids this environment to select for drought, when in fact, I don't have any drought. In many situations, or the drought stress levels compared to another environment is very, very poor. So I think that doing the decision or going a little bit backwards on this idea on trying to develop an envirotyping initiative, and then again, emphasizing that for doing an excellent envirotyping, what do we need? Excellent weather data and really good soils data. And even more importantly, sometimes we don't even have this, even excellent field and crop data, phenology, detailed studies. And in many situations, we are in the point of pushing our science into doing multi-environment trials with not detailed collection. When in fact, we should do probably in some situations, depending on the objective, studies that are more focused on details, that we can collect data so we can then make that data to be reproducible, that we can then explore and understand what are the main factors causing the yield impact.
Great, thank you so much. And that also addresses another question, which is about how close are we in integrating the models in the crop performance data, for example, and so you already addressed that question in a sense.
Yeah, we have a study, I mean, around, I will follow up with you, that we are doing an envirotyping for sorghum. So
okay. I'll close in. My last question to you is that I really like your idea about field memory, right? And then to predict for yield persistency. But this would require a significant change in our thinking in terms of data sharing and making the data available for public to use it. So what's your take on that?
I think that is coming, right? I mean, if you look at what the research grants institutions are moving in that direction. The first movement or the first change came with the idea of all our publications should be open access. No, the second shift came with the idea of saying now we need to put all the data in repositories. Now the final shift is grants or some office are asking us to open our codes and to share the codes. So whether we will like it or not, I think that maybe the change sometimes it needs to be, maybe some people would not like to hear this, but it needs to come from someone forcing a little bit. I think that if the concept and idea and the end goal of this is novel, we should start doing it, because in many situations, and I can say by experience, when I work with my students and we try to do synthesis analysis or reviews, we go back in time to really excellent data sets from the 60s, 70s, 50s, and 40s, and we start seeing all the problems that we face because we are not able to secure that legacy, the legacy of opening that data and making sure that it's relevant for everyone. And then we are duplicating the studies again. We're doing those studies again because we are not able to access to some of these relevant data sets. So sooner or later, the change will come. I know that security is a concern, privacy is also a concern, but I think that we have some mechanisms of, basically data protection or some other things that we can put in place to make sure that the people feel comfortable doing that.
And also, I think with the farmers also like taking this imaging over the time, they'll have to make sure those repositories are available. And then when we give them the tool, they need to use their own data for machine learning and other types of modeling to make sure that tool gives them the right prediction or right prescription to manage the field. Thank you so much. With that, thank you so much for your nice presentation. Let's give a virtual round of applause for Ignacio. And again, this presentation is being recorded, and I'll make sure that it's available to all the Sigma Xi members in future. Thank you very much for your time. I appreciate it. Thank you. Take care.
Thank you.